All right, let's try evaluating one of these triple integrals, but using cylindrical coordinates. So, first of all, let's think about here our z. Start with z first. Well, fairly obvious. So we're going below the plane x plus 2, and we could try attempt to draw that out, but it's just kind of an angled plane. But we want it above the xy plane, which the xy plane would be z equals 0. So that pretty well designates that z is going to go from that 0 up to that plane. Spells it out, so hopefully that's seems okay. Is that all right? Make sense? Now, we're going to change though to cylindrical coordinates, and so cylindrical coordinates are like the three-dimensional polar coordinates, and so in you have z's in cylindrical, right? But you have r theta in z. You don't have x's and y's. And so we need to change, the only thing here then would be to change the x over to r's and thetas. X is r cosine theta. So that's what z will be. R cosine theta plus 2 would be the upper limit of the z. Okay? All right. Now, the other part to it, the r and theta, well, of course, that's going to come here. You know, we can initially, since these are initially in x's and y's, start with that in the xy plane. Okay, so those are just circles, right? Radius 1 circle, radius 2 circles centered at might be the best 2 circles drawn in a while. But anyway, but we don't want the x's and y's, we want the r's and thetas. And you can see why here it's kind of advantageous to do r's and thetas instead of x's and y's, because that would be kind of a mess to get x, you know, what x goes between and what y goes between. You know, we're going to have to do some breaking things up because we're going all the way around. So we want the part in between it. You know what I'm saying? That would be a mess in that. So that's why this one's a lot better in r's and thetas, because for example, theta's easy. I just want 2 pi, right? Start from 0, go to 2 pi. Because it does go all 360 degrees around, right? What about the r? Well, the r, you just think about r is the radius here, if you will, how far out you go. Well, that's very easy because this is this right here would be r is 1, that was r is 2, right? Because that's the radii of the circle there. So r very easily is just from 1 to 2. Since they're just circles, they're not even functions of theta. You know, sometimes we have r's that are function of theta. Here it's just 1 and 2. Okay. So that's a whole lot better than x's and y's, and so that's the advantage of this here. So our triple integral then, so dv, well, let's start with this. So y, so we've got to convert that to, unfortunately it's y squared, but y is r sine theta, so y squared would be r squared cosine squared theta. And then what about the dv? If I go to cylindrical, what does dv equal in cylindrical? it's all these, but there's an extra R, right? You do an R, and usually the order is DZ, DR, because, in this case it wasn't, but a lot of times, sometimes R's are in terms of thetas, functions of thetas. Anyway, that's what. So this is y squared, and then that R again is just from the way you have to convert it. Anyway, all right, and so yeah, we got the z's first, so the z's go from 0 to r cosine theta plus 2. Then we're doing the r's. R's goes from 1 to 2, and then theta is 0 to 2 pi. Is that good? That's a triple. All right, so let's evaluate this one. Start with the z's. Well, good news is, starting off anyway, good news. There is no z to contend with there, and so the interval of that thing will just be r cubed. Let's go ahead and put that together. Cosine squared theta. But those are just constants, and so the antiderivative is just z. Then we have to plug in the z, 0 to r cosine theta plus 2. And now that's where the easy part ends, I guess. Because this will be r cubed cosine squared theta times r cosine theta plus 2. Of course, z is 0. That's nice. A little bit nice. Okay, well, yeah, so that not going to be too bad here. Because next, what do we do? The r's? Well, we probably go ahead and multiply that in. So it'd be r to the 4th cosine cubed theta plus 2r cubed cosine squared theta. Yeah, then we'll do the antiderivative with r. So that would be 1/5 r to the 5th cosine cubed theta plus 1/4, 2 times 1/4, so it'll be a half r to the 4th cosine squared theta, and the r's 1 to 2. So far not too bad. I think we saved the last, best for last. Yeah, these are r's. So plug in r to be 2, so that'd be 1/5 times 32, that'd be 32/5 cosine cubed theta plus half of 16 to be 8 cosine squared theta. And then we've got 1 for the lower limit, so it'd be 1/5 cosine cubed theta, and then plus a half cosine squared theta. All right. Yeah, so good news is there are some like terms, if you will. 32/5, that'd be, that's just me 31/5. 31/5 cosine cubed theta. And then 8 minus a half cosine squared. 15 halves cosine squared. Well, again, if nothing else, just kind of review powers of how we do the antiderivative powers. Remember a little bit? Yeah, it turns out this one's not too bad. You can do some U substitution. You just have to break it up into cosine squared theta times cosine theta, and then d theta. We'll do the other one separately here. On the I guess we'll go ahead. On the 15 half, on the cosine squared, the even powers, that's where you have to use that double angle. Let's see, cosine is 1/2 minus 1/2 cosine of 2 theta. So that will knock that out pretty easy. But here, now you convert that to just kind of review. It's been a while since we did this. Convert that to 1 minus sine squared. Then it's just a u substitution. U equals sine theta, du equals cosine theta, d theta. There you go, that's du. So we've got 3/1/5. So we got 1 minus u squared. U. So we got 31/5 times u minus 1/3 u cubed, which is 31/5 times sine theta minus 1/3 sine cubed theta. All right. Then like I said over here, that's just 15/4 minus 15/4 cosine 2 theta. The only deal is on this one, a little u substitution there, but it turns out it's a half. So this will be 15/4 theta minus 15/4. Then you'll have that half because of the u substitution. Antiderivative cosine is sine 2 theta. And then that's evaluated from 0 to 2 pi. Good news, a lot of these are zeros. Sine of 2 pi is 0, so all this is 0 here. 15/4 times 2 pi, you gotta plug that in. But then you have sine of 4 pi, that's 0. And then plug in the zeros, well sine of 0 is 0, so that's all 0. 15/4 times 0 is 0. Sine of 0 is 0, so yeah. It's 15x pi. Anyway, yeah, I mean, it's a triple interval. You're going to run into some difficulties finishing the problem. All right, these other two I wanted to show you. Let's just set these up. Get them set up here. Is it okay? Any problems or concerns? Let's convert to cylindricals. Talk about one of those. All right, so we got -1 to 1 is first, 0 to the square root of 1 minus y squared, and then x squared plus y squared to the square root of x squared plus y squared, x, y, z, dz, dx, dy. All right, so we've already got the Cartesian, if you will, version. We want the cylindrical. Version of it. So again, cylindrical, that's r, thetas, and z's. Well, of course, Yeah, we've got the conversion for x and y. That won't be hard. dz, dx, dy. We know that's r. dz, dr, d theta. So the only thing then is figuring out what these limits change to if we do that. So looking at them, all right, so the y's are -1 to 1. The x's are 0 to square root of 1 minus y squared. And the z's are from x squared plus y squared to square root of x squared plus y squared. Well, good news. Yeah, what we need to do is, all right, so z's here are in terms of x's and y's. We want it in terms of r's and I guess thetas, potentially, but very easy here, hopefully easily see. X squared plus y squared, what does that equal in terms of r? R squared, right? And then z's are the square root of x squared plus y squared would be the square root of r squared, which is r. So you're with me there. That's pretty easy. It's not bad. Well, so that leaves me, well, I got to figure out then, so that basically turns, converts it over for the z's, z part of it. How do I the rest of it? Well, I need to look at this again in the xy plane, and that probably will help me on my r's and thetas. That's the ranges of z, limits for z. So x equals 0, we know that's just, whoops, sorry, x equals 0 is the y-axis. So that leaves me x equals the square root of 1 minus y squared. What does that look like? Well, it's similar to y equals 1 minus x squared, which is, that's a semicircle, the top half of a semicircle. This is, I've exchanged the x's and rows of the x's and y's there, and I think we might have done this. Did we do that one? What is that? Remember what that one was? I think we did that one last time. This is the top half, semicircle, top half of the circle. This is actually the right half of the circle, radius one. So depends on which one you have solved for. If you got it solved for y, then it's the top half. It's not for x, it's the right half. All right, so that's what it looks like, and then of course the y, yeah. So the y's are no surprise there. We're going from -1 to +1 for the y's. All right. So what we need then is we need our r and theta range here. So what do we want to do there? So again, theta is the angle that we sweep out. To get this graph. So when we start at this angle, what do we say that angle is? -π/2. And then it goes all the way around to +π/2. All right, then, easy enough on the r's. The r's are going to range, so, start here and then go back to that. Just be r0, 1, right? Easy enough there. So, this triple integral then would be in cylindrical. All right, so again, let's start with our function here. We've got x, y, z. That's our function. X is our cosine theta. Y is our sine theta. And luckily, z is z. Now, again, like we said, this is dV, and in converting to cylindrical, the dV is R, usually dz, dr, d theta. So you got that extra R thrown in there, so we got to add the R, and then dz, dr, d theta is usually the order we want to go with that. So putting the limit, so the z's are first, well, z's are r squared to r. R's are next, that's 0 to 1, and then theta's negative pi over 2 to pi over pi over 2. And then you evaluate it accordingly. It's a bit of a process just to get there, but it pays off. Maybe not an easy triple integral, but it's easier than what we had, probably. All right, question or concern on that? Okay, let's do one more of these. Okay, so let's find the triple integral in the cylindrical coordinates. That would give us the volume that, this is interesting, all right, that lies within both the cylinder x squared plus y squared equals 4 and the sphere x squared plus y squared plus z squared equals 9. Don't know that we've done a whole lot of spheres here lately, but we talked about it way back when, but here's another chance. Okay, so yeah, so this is interesting. What we've got is a cylinder, kind of, well, yeah, we've got a cylinder, but the tops, you know, a cylinder, we have a flat top and a flat bottom, right? Here, what we're saying is we're kind of capping it off with this. So we've got this sphere, and the sphere, that would be a sphere radius 3, right? What that would be. So we got a radius 3 sphere. Well, what's the radius of my cylinder? That'd be a radius 2 cylinder, right? So yeah, it kind of goes inside here because it's radius 2, this is radius 3 sphere. So you've got this cylinder inside there. But the thing is, if you think about the top of that cylinder, it's rounded off, you see. And unfortunately, it's not a hemisphere, a avosphere. It's just the kind of the little piece of the sphere that enters. So it's kind of an unusual volume. So you got a cylinder volume, but then you've also got this little bit of a sphere cut off at the top of it. You know what I'm saying? I don't know if you're getting the visual or not, but it's interesting. We can find this volume using the triple integral. All right. So how do we do it? Well, we know that with the volume, Cartesian-wise, you just do 1 dV, right? But we want to do this in cylindrical, since we definitely have a cylinder involved in a sphere, but let's see if we can figure that out. Okay. One good thing, note here, the z's, all right, so cylindrical again, you want z's and thetas and r's, right? That's the 3 ones you want. The good news is, if you think about it, you know, the Z's here, with the way this is a, you know, the cylinder is just vertical, kind of parallels the Z axis. If you'll notice, the Z's actually just go from here up to the top of the sphere. So from this bottom of the sphere to the top of the sphere. Now, again, you have to kind of look at it. You got the top half and the bottom half of the sphere. Now, good news is here, look at this. So here's our sphere. So I need to go from the top half of the sphere to the bottom half of the sphere. But the good news is, you know, convert to z, thetas, and r's. What is x squared plus y squared? That's r squared, isn't it? And so, getting that top half and the bottom half, that's not too bad, because here's going to just be plus or minus the square root of 9 minus r squared. So the bottom half will be the minus, and the top half will be the positive square right there. So z is going to range from negative the square root of 9 minus r squared to positive 9 minus r squared. All right, but that leaves the r's and thetas. And again, the r's and thetas come from the xy plane. And if you think about it, in the xy plane, what we're going to be dealing with here is your, think about your cross section here. You're just talking about, because this really has no role, it's just the circle. As you think about, you know, wherever cross section piece there, you're just talking about the circle. X squared plus y squared. And so what would that be in r and theta? Well, theta is just going to go 0 to 2 pi. And then r would go from, you know, covering the whole region, so r goes from 0 out to the circle, which is just radius 2, isn't it? Is that okay? And so that's my limits for all of them. Now the only thing is, again, dv is r, dz, dr, d theta. The z's, we know, negative square root of 9 minus r squared to positive 9 minus r squared, square rooted. Then we do the r's, 0 to 2. And then theta is 0 to 2 pi. So that would give us the bottom. Not too bad. If you guys have to go ahead and evaluate this, notice this is going to work out pretty nicely, because when I do, well, you know, the z's, it'd be RZ, but which will give me a pretty, looks pretty bad, but notice it'll be this. Just to, I'm not going to do it all the way out, but actually it'd be plus R. So we have 2 of those. So that's one thing, we have 2 of those. But notice that's a very nice U substitution when I have to do that. So anyway, preview that one. Okay. All right.